Okay, next we're going to look at some exceptions to the rules that we've learned so far for electron configurations. There's quite a few that occur, especially in the D subshells and the F subshells, but the two main exceptions that we're going to look at really have quite a bit of significance. The other ones don't really. So that's why we're only going to cover these right here. So we'll start with chromium and molybdenum. So chromium and molybdenum are in the same column. Chromium has 24 electrons. Molybdenum has 42 electrons. Okay, so let's do chromium first. So we're going to do the noble gas notation. So we're going to start with argon, 18 electrons. Then we're going to go to 4s, okay, 4s2. And then we'd go to 3d4 to get all 24 of our electrons, okay? So that's what we've been doing, but this is actually not what we're going to do here. So for the transition metals, it's more stable to have a half-filled D subshell than it is to have a fully filled S subshell. So what we do here is we take, let me erase this here, we take one out of the S and we put it into D. That way we have a half-filled D subshell. So our, just to show you, 1, 2, 3, 4, 5. So here's the orbital diagram. So we would have one in the 4s and then one in each of our D orbitals. So this is a lower energy state and it's more stable. So that's why it does it. So molybdenum actually does the exact same thing. So molybdenum is just lower in the column. And so we start with krypton here. Go to 5s and then 4d. But again, because it's more stable, we're going to take one out of the S and put it into D. So they actually have pretty much the same electron configuration. The only difference is the shells. So here we have 5s, 4d, so 1 in 5s and 1 in each of the 4d orbitals. So that only happens with chromium and molybdenum, to take one out of the S and put it into the D to get a half-filled D subshell. So next we're going to look at copper and silver. So copper has 29 electrons and silver has 47. And again, they're in the same column. So we'll start with copper first and do the noble gas notation. So we're going to start with argon, go to 4s2 and 3d9. So again, that's normally what we would do, but here it is more stable for the D subshell to be fully filled than the S subshell to be fully filled. So we're going to take, again, one out of the S and put it into the D. So now we have a fully filled 3, 4, 5 D subshell. So we're going to get one in the S, and then D is going to be completely filled. Okay, so then silver looks exactly the same, except it's just lower on the period. So we get 5s2, 4d10 or 4d9. But again, because it's more stable, we take out of the S and put it into the D. So we're going to get only 1 in 5s and 10 in 4d. So fully filled D subshell. So this only happens for copper and silver. So I don't want you to start taking out of the S and putting it into D. Okay, this only happens for copper and silver, and then the other two were chromium and molybdenum. So those four are the only ones that have electron configurations that don't follow the rules that we've talked about so far. Okay, so the reason that the two had similar electron configurations is because groups actually have similar electron configurations. So if you look in group 1 there, they have similar electron configurations where they all end in S1. So hydrogen is 1s1, lithium 2s1, sodium 3s1, underneath would be potassium would be 4s1. So the ending of their electron configuration is very similar. So all of the columns that you look at, the only difference is going to be the shell they're in, but they all have similar endings in their electron configuration. And you can see, because they have similar endings in their electron configuration, they also have the same number of valence electrons. So all of group 1 has 1 valence electron. All of group 2 has 2 valence electrons. So remember, those are the ones in the outer shell. So the highest shell number are the valence electrons. Okay, we're going to look at a few periodic trends. So first is the effective nuclear charge. And the effective nuclear charge is just first of all, we'll talk about the nuclear charge. The nuclear charge is the positive charge of the nucleus. So how many protons you have in your nucleus, that's the nuclear charge. Then the effective nuclear charge is the positive charge that is felt by the outer electrons. So those valence electrons we were just talking about. So what happens is the core electrons kind of shield the nucleus from the outer electrons. So those valence electrons don't feel as much of a positive charge as the core electrons do. So there's a simple way to measure the effective nuclear charge, and there's also a more complicated way, but we're just going to cover the simple. So we're going to take the atomic number, which is Z, and we're going to subtract out the core electrons, and that's going to give us the effective nuclear charge, what those outer shell electrons are feeling. So if you look at, we'll start with lithium. So lithium right there at the bottom is on our example. So lithium has an atomic number 3, and it has 2 core electrons. So we subtract those, and we get a positive 1 charge. And then go over to beryllium. Beryllium's right next to lithium. So beryllium has 4 electrons and 2 core electrons. So 4 minus 2. So beryllium has a +2 effective nuclear charge. And then over to boron. Boron has 5 electrons and 2 core electrons, so we get a +3. So you're seeing the pattern here. So group 1 has a +1, group 2 has a +2, group 3 has a +3, and then look at group 4. 6 minus 2 gives us a +4, group 5 has a +5, group 6 a +6, and group 7 a +7. So you can figure out their effective nuclear charge just by what group they're in.